Welcome to the sleepy Milky Way. If you are here right now, settling in for the evening, perhaps with the lights turned low and a quiet room around you, then you have found exactly the right place. This channel is a space built slowly and carefully for those who love the gentle vastness of the cosmos, for the quiet explorers, the late-night wanderers, the people who find comfort not in noise or urgency, but in the soft, unhurried unfolding of ideas that are simply too large to rush. Here, we travel together through galaxies and nebulae, past planets and moons and ancient light, not racing toward any destination, but simply drifting, the way a leaf drifts on still water, carried gently by the current of curiosity. If this kind of journey speaks to you, we would be quietly glad to have you stay, to subscribe, to settle in, and to become part of this small community of calm travelers who have chosen to spend their evenings among the stars. Every week, we return to this space together, drawn by the same gentle pull that has always drawn human beings outward, the pull of wonder, of patient inquiry, of the desire to understand the enormous and beautiful universe we find ourselves inhabiting. So, make yourself comfortable, let your breathing slow, and let us begin. Tonight, we are going to sit with a question that sounds, at first, almost too simple to carry much weight. It is the kind of question that arrives softly, almost apologetically, as though it knows it is about to open a door into something unexpectedly deep. The question is this: what would actually happen if Earth suddenly stopped moving through space? Not spinning. We are not talking about the familiar rotation that turns day into night. Not orbiting in isolation. We are not asking only what would happen if Earth fell out of its path around the Sun, though we will spend a great deal of time with that particular scenario before the evening is done. We are asking something quieter and more philosophically interesting than either of those things in isolation. We are asking about all of the motion, every last layer of it, the whole nested architecture of movement that Earth carries through the cosmos at every moment, and what the universe would look, feel, and become if all of that motion simply, gently ceased. It is a thought experiment, of course. It could not happen in any conventional physical sense, and we will come to understand exactly why that is true as we move through this long, unhurried evening together. But thought experiments are some of the oldest and most productive tools that science has ever known. Einstein himself spent years thinking about what it would mean to ride alongside a beam of light. And from that quiet mental exercise, the entire architecture of special relativity eventually emerged. So there is nothing wrong with sitting with an impossible question, turning it over carefully in the mind, asking not how we would make it happen, but what it reveals about the machinery of the universe simply by being asked. To begin, we should take a moment to truly understand just how much motion Earth is carrying right now, in this very instant, as you listen to these words or read them in the quiet of your room. Because the answer is somewhat more layered than most of us realize in our daily lives, and each layer of motion, once properly appreciated, opens into its own world of consequences, history, and meaning. Most of us are aware, in a background sort of way, that Earth rotates. We know that the surface of the planet beneath our feet is turning, carrying us from day into night, and back again in a cycle that has been so consistent throughout human history that it forms the very foundation of how we measure time. At the equator, The surface of Earth moves at roughly 1,670 kilometers per hour, a speed well beyond what any ordinary aircraft can match. Those of us who live at higher latitudes move somewhat more slowly because the circumference of the circles we trace each day is smaller. But we are all moving, all spinning, all participating in this rotation that has been ongoing since before there were eyes to watch the sunrise or minds to wonder at the turning of the sky. The rotation is so embedded in our experience of the world that we barely notice it. We notice only its effects, the rising and setting of the sun, the wheeling of the stars through the night, the Coriolis deflection of winds and ocean currents that shapes the weather and the climate of the entire planet. Then there is the orbital motion. Earth moves around the sun in a path that is not quite a perfect circle, but rather a gentle ellipse, slightly elongated, with the sun positioned not at the center of the ellipse, but at one of its two foci. This means that Earth's distance from the sun varies slightly over the course of the year. We are closest to the sun at a point called perihelion in early January, and farthest at a point called aphelion in early July. The difference is modest, about 5 million kilometers, or roughly 3% of the average distance, and it has a modest effect on the amount of solar energy we receive. But it is a real variation, and it is a consequence of the fundamental geometry of gravitational orbits, that no orbit in an inverse square gravitational field is perfectly circular unless placed there with extraordinary precision. To travel the entire ellipse of its orbit in a single year, Earth must move at an average speed of about 107,000 kilometers per hour, or roughly 30 kilometers every second. That number is worth sitting with for a moment. 30 kilometers per second. In the time it takes to draw a single calm breath, Earth has carried you through nearly 90 kilometers of space. In the time it takes to speak this single sentence at a slow and measured pace, Earth has moved several hundred kilometers along its orbital path. This motion is silent, unfelt, imperceptible to our senses, yet it is happening continuously, without interruption, and has been happening for 4.54 billion years. But the orbital motion around the Sun is only the second layer of movement, and there are more to come, each one larger and quieter and more encompassing than the last. Our entire solar system, the Sun with all its planets, moons, asteroids, comets, and the faint haze of particles that extends far beyond Neptune, is itself moving. It is orbiting the center of the Milky Way galaxy, tracing an enormous path around the massive concentration of stars and gas, and, at the very heart, a supermassive black hole known as Sagittarius A star. The solar system travels this galactic orbit at a speed of approximately 220 to 250 kilometers per second, which translates to somewhere around 828,000 kilometers per hour. At that speed, you might expect the journey around the galaxy to be brief, but the Milky Way is a structure of such vast scale that even moving at this extraordinary pace, one complete orbit takes between 225 and 250 million years. Astronomers call that span a galactic year, and in the entire history of Earth, our planet has completed only about 18 or 20 of them. The solar system was last at its current position in the Milky Way when dinosaurs had barely appeared on Earth, when the Triassic period was just giving way to the Jurassic, when the continents were still arranged in configurations quite different from the ones we know today. And in the galactic year before that, there were no dinosaurs at all. Only the strange, sprawling life of the Permian period, before the greatest mass extinction in Earth's history, reshaped the story of life on this planet. Even that is not the final layer. The Milky Way itself is moving. Our entire galaxy, a structure containing hundreds of billions of stars, is drifting through space in relation to other galaxies, other galaxy clusters, and the great cosmic web of structure that fills the observable universe. Our galaxy and its neighbors form a collection called the local group, a gravitationally bound assembly of roughly 50 to 80 galaxies, spread across a volume roughly 10 million light-years in diameter. The two largest members are the Milky Way and the Andromeda Galaxy, and they are currently approaching each other, drawn together by their mutual gravity on a course that will eventually result in a slow and graceful merger billions of years from now. The local group itself is moving through the larger cosmic web. It is being drawn toward a vast concentration of mass known as the Great Attractor, an overdensity of galaxies and dark matter located roughly 250 million light-years away. The motion toward the Great Attractor is only part of an even larger scale flow, as our region of the universe participates in what cosmologists call the bulk flow, the slow, large-scale drift of matter along the filaments and sheets of the cosmic web, drawn by the gravity of the greatest concentrations of mass in the observable universe. When astronomers measure the faint afterglow of the Big Bang, a soft, pervasive radiation that fills the entire sky at microwave wavelengths and is known as the cosmic microwave background, they can detect a very subtle asymmetry in its temperature. One side of the sky appears ever so slightly warmer, the other ever so slightly cooler, and that asymmetry is the signature of our own motion relative to the universe's deepest available reference frame. From that measurement, scientists have determined that our solar system is moving at approximately 370 kilometers per second relative to the cosmic microwave background, and the local group as a whole moves at around 627 kilometers per second relative to that same reference frame. These are not small velocities. They represent real measurable motion through the cosmos, written in the temperature of the oldest light in the universe. So, when we ask what would happen if Earth stopped moving through space, we are really asking about the removal of all of this. The spin, the solar orbit, the galactic orbit, the drift through the local group, the bulk flow toward the Great Attractor, and the deepest layer of peculiar velocity relative to the primordial light of the Big Bang. We are asking about an object that, in our thought experiment, would be rendered genuinely stationary relative to the largest reference frame we know. Before we explore what the consequences of that cessation would be, it is worth pausing to address a question that physics itself raises almost immediately when we pose our thought experiment. What would it even mean to be stationary? This is not a trivial question. In fact, it is one of the most foundational questions in the entire history of physics, and it has been answered in ways that feel, at first, deeply counterintuitive, even slightly unsettling, before they settle into a kind of clarity that is, in its own way, more elegant than the simpler picture it replaced. For most of human history, people naturally assumed that there was some fixed, absolute background to the universe, some grand stage on which all motion occurred. If you were moving relative to that stage, you were truly moving. If you were at rest relative to it, you were truly still. This idea was so natural, so embedded in the everyday experience of living on a solid planet with a sky above it, that it rarely needed to be stated explicitly. Of course, there was a background. Of course, there was a standard of absolute rest. The only question was where that standard resided and how to access it. Isaac Newton himself believed in something like this, a conception of absolute space and absolute time that formed the invisible scaffold of all physical reality. In Newton's universe, space was a fixed, infinite, empty container, and time flowed uniformly from past to future at the same rate everywhere, independent of any observer or any physical process. Objects moved through this absolute space, and their motion relative to it was their true objective motion, independent of any other object. The question of whether Earth was truly moving had, in Newton's framework, a definite and objective answer. But as the 19th century gave way to the 20th, and as a series of elegantly designed and meticulously executed experiments failed to find any evidence of this absolute background, the understanding of motion began to shift in a quietly profound way. The most famous of these experiments was conducted by Albert Michelson and Edward Morley in 1887, and its goal was to detect the motion of Earth through the luminiferous ether, the hypothetical medium through which light was supposed to travel, the absolute background that would define true rest and true motion. The experiment was extraordinarily precise by the standards of its time, and it found, to the considerable puzzlement of the physics community, absolutely nothing. No evidence of motion through the ether, no difference in the speed of light in different directions. The ether, if it existed, left no detectable trace. The resolution of this puzzle came in 1905 when Albert Einstein published his special theory of relativity. Einstein built his entire theoretical architecture on a single, deeply considered premise: that the laws of physics are exactly the same in every reference frame that moves at a constant velocity. There is no experiment you can perform, no measurement you can make, no observation you can achieve that will tell you whether you are truly at rest or truly moving at some constant speed, because the distinction simply does not exist in any physically meaningful sense. Motion is always relative, always a comparison between two things, never an absolute property of a single object considered in isolation. This principle, the principle of relativity, was not entirely new. Galileo had recognized something similar centuries earlier. If you are in a ship's cabin with no windows, moving at constant speed on a calm sea, no mechanical experiment can tell you whether the ship is moving or still. A ball thrown straight up returns to your hand just as it would on shore. A pendulum swings at the same rate. Water pours the same way. Everything is the same, not because the motion is too slow to detect, but because there is genuinely nothing to detect. Constant velocity motion has no mechanical consequences within the frame that shares that motion. Einstein extended this principle to include electromagnetic phenomena, including light. He recognized that if the speed of light were the same in every inertial reference frame, a conclusion that both Maxwell's equations and the Michelson-Morley experiment seemed to demand, then space and time could not be absolute and universal. They had to be relative, to vary between observers in motion relative to each other, in exactly the way that preserved the constancy of the speed of light for all observers. The resulting theory described a universe in which time runs at different rates for observers in relative motion, in which lengths are contracted along the direction of motion, in which simultaneity is not universal but depends on the observer's state of motion. These are not mere theoretical abstractions. They are effects that have been measured repeatedly and precisely in experiments involving particle accelerators, atomic clocks on aircraft, and the decay rates of cosmic ray muons reaching the surface of Earth. In this relativistic universe, the concept of absolute rest dissolves. There is no privileged reference frame, no cosmic background relative to which all motion is measured, no answer to the question of whether you are truly moving or truly still. The cosmic microwave background provides the closest practical approximation to a universal reference frame. But even it is not absolute in the philosophical sense. It is simply the frame in which the distribution of background radiation looks most uniform, the frame that moves with the average flow of matter in the expanding universe. Any observer in any frame has an equally valid claim to be at rest, and the laws of physics will look the same to all of them. This means that the most honest answer to the question of what would happen if Earth stopped moving through space begins with a gentle clarification. Stopped relative to what? The velocity relative to the Sun is a specific, physically meaningful number associated with specific gravitational consequences if it is removed. The velocity relative to the galactic center is a different number associated with different and much slower developing consequences. The velocity relative to the CMB is yet another number associated with consequences so slow and remote that they would be undetectable on any human timescale. For the purposes of our thought experiment, we will work through each of these scenarios in sequence, from the most immediately consequential to the most cosmological, taking our time with each one, exploring not just the physical consequences, but the deeper principles of physics and astronomy that each scenario illuminates. Let us begin with the most familiar and the most immediately consequential scenario. What would happen if Earth's orbital velocity around the Sun was suddenly reduced to zero? An orbit is not a thing that simply happens to an object that happens to be near a massive body. The object is always falling toward the center, but always missing it, because the curved surface of space is constantly receding beneath it as it moves sideways. To understand this, it helps to think of the old thought experiment of firing a cannonball horizontally from a very tall mountain. If the cannonball is fired slowly, it curves toward the ground and hits the surface relatively quickly. As the firing speed increases, the cannonball travels farther before hitting the ground. At some specific speed, the orbital velocity, the ball falls toward the curved Earth at exactly the same rate that the Earth's surface curves away beneath it, and the ball never reaches the ground. It simply keeps falling in a great circle forever, or until it hits something, or until the frictional drag of the thin upper atmosphere slows it down. Earth orbiting the Sun is this same process, scaled up by a factor of 100 million. Earth is falling toward the Sun continuously at every moment, but it is also moving sideways at 30 kilometers per second, and it is moving sideways fast enough that the Sun's surface always curves away beneath it just as quickly as Earth falls toward it. The result is the elliptical orbit, the year-long path that Earth has traced through the solar system for billions of years without interruption. When we imagine removing Earth's orbital velocity, reducing it from 30 kilometers per second to 0 relative to the Sun, we are removing the sideways motion that maintains this balance. Without the sideways velocity, there is nothing to oppose the inward pull of solar gravity. Earth would begin to fall. Not fall dramatically, not plummet suddenly in the way a dropped object falls in our everyday experience. Fall slowly at first, because the Sun's gravity, while powerful, acts over a great distance, and at Earth's present distance from the Sun, roughly 150 million kilometers. The acceleration due to solar gravity is only about 0.006 meters per second squared. A gentle pull, by the standards of surface gravity, which accelerates objects downward at 9.8 meters per second squared. But it is a consistent pull, and it would begin to accelerate the now stationary Earth directly toward the Sun, and over the course of days and weeks, the velocity would build. The acceleration would increase as Earth drew closer, and the planet would trace a long, direct, radial path inward toward the star. The duration of this inward journey can be calculated using Kepler's third law, by treating the radial fall as half of a degenerate ellipse, an ellipse so flattened that it has collapsed to a straight line. The semi-major axis of this hypothetical ellipse would be half the original orbital distance, roughly 75 million kilometers, and the orbital period would scale with the 3/2 power of the semi-major axis, in the same way that all orbital periods do. The result comes out to approximately 65 days for the complete infall, though the last stages of this journey would be much more rapid than the early ones, as the increasing proximity to the Sun drives a dramatically increasing gravitational acceleration. What would those 65 days look like on the surface of Earth? In the early stages, very little would change. The Sun would appear no larger than usual. The seasons would pause in their familiar progression. The sky would be the same blue, and the nights the same dark velvet. The ocean temperatures would be essentially unchanged. The weather patterns of the planet would continue to operate in roughly their normal way. A careful astronomer might notice that the Sun's parallax against the background stars was beginning to shift slightly, indicating that Earth's position relative to the Sun was changing. But for anyone simply going about their daily life, the first few days after the hypothetical stopping would be indistinguishable from normal. Slowly, over the first couple of weeks, the Sun would begin to grow in apparent size. Its angular diameter would increase as Earth drew closer, and with it would come a gentle, then increasingly noticeable increase in the solar flux, the amount of solar energy arriving at Earth's surface per unit area. The oceans, with their enormous thermal capacity, would absorb much of this additional energy without showing a dramatic temperature increase at first. Atmospheric temperatures would begin to rise more noticeably in equatorial regions, where the Sun was most directly overhead. The polar regions, receiving sunlight at a shallower angle, would warm more slowly. As the weeks passed, the changes would become more pronounced. The weather patterns that depend on the temperature gradient between equatorial and polar regions would intensify as the tropics heated faster than the poles. The circulation of the oceans, which normally moderates temperatures and redistributes heat across the planet, would work harder to cope with the increasing energy input. Precipitation patterns would shift as more water evaporated from the warming oceans, increasing atmospheric humidity and altering cloud cover in complex ways. The complex, coupled system of atmosphere, ocean, and land surface would respond in ways that are difficult to predict in detail, but the overall direction would be clear: warming, intensifying, escalating. By the third or fourth week, the sun would look noticeably different in the sky: larger, brighter, more insistent. Surface temperatures in equatorial regions might be approaching levels beyond what life can comfortably tolerate. The ice caps would be melting rapidly, adding fresh water to the oceans and altering their circulation. The snow cover at high latitudes would retreat, reducing the planet's reflectivity and allowing even more solar energy to be absorbed by the darker surfaces beneath. These feedback mechanisms, the ice albedo feedback, the water vapor feedback, the various responses of vegetation and clouds, would amplify the initial warming in ways that would progressively accelerate the change. By week 5 or 6, conditions at the surface would be dramatically different from anything in human experience or any geological record of the Holocene. Temperatures in equatorial regions might be approaching or exceeding the wet bulb temperature limits beyond which the human body cannot effectively cool itself. The ocean's surface in the tropics would be significantly warmer, feeding violent weather systems with more energy than they have ever had available. The atmosphere would be thickening with water vapor, itself a greenhouse gas, which would trap additional heat and push temperatures still higher. In the final days of the journey, as Earth approached the Sun more closely than Venus ever does, conditions would pass beyond the point where liquid water could exist at the surface. The oceans would begin to boil. The atmosphere would become a thick, hot steam. The surface rocks would heat from above as well as from within, and the geology of the planet would begin to respond to the extraordinary temperatures in ways that would erase all surface features over time. By the time Earth finally reached the Sun, after approximately 65 days of this long, accelerating fall, it would have been transformed from a life-bearing world into something that more resembled a glowing cinder, stripped of its water and atmosphere, its surface remade by heat and radiation into something barely recognizable as the same planet that had set out from its normal orbital position 2 months earlier. But this scenario, as vivid and physically grounded as it is, still only addresses one layer of the motion question. We have asked what happens when the orbital velocity around the Sun is removed. We have not yet asked what happens when the solar system's motion around the galactic center is removed, or what happens when the galaxy's motion through the local group is removed, or what the deepest cosmological layer of motion implies for the thought experiment. Each of these scenarios is interesting in a somewhat different way, and each opens a different window onto the physics and philosophy of motion, gravity, and cosmic structure. So let us continue outward, layer by layer, with the patience and the calm attention that the topic deserves. The solar system's orbit around the Milky Way galaxy operates on a fundamentally different scale from the Earth-Sun orbit in almost every dimension. The orbital radius is roughly 26,000 light-years, a distance so large that it requires the light-year, itself an enormous unit, to express it in manageable numbers. The orbital period is hundreds of millions of years. The orbital speed is 7 to 8 times faster than Earth's speed around the Sun, and yet the sheer vastness of the orbit means that it takes incomparably longer to complete. These numbers, taken together, reveal a gravitational landscape of extraordinary scale, one in which the Sun and its entire system are simply one small object among hundreds of billions. all participating in the same slow, majestic circulation around the gravitational center of the galaxy. The center of the Milky Way is a region of extraordinary density and activity. The central few hundred light-years contain a dense concentration of old stars, molecular clouds, and regions of intense star formation. At the very heart, there is the supermassive black hole Sagittarius A star, with a mass approximately 4 million times that of the Sun. This black hole does not actively consume large quantities of material at the present time. It is relatively quiet compared to the active galactic nuclei seen in other galaxies. But its enormous mass shapes the dynamics of the galactic center profoundly, and occasional flares suggest that it does periodically receive and consume small amounts of material. The gravity that governs the solar system's galactic orbit is not, however, primarily the gravity of the central black hole. At a distance of 26,000 light-years, the black hole's direct gravitational contribution is actually quite modest compared to the cumulative gravitational effect of all the stars, gas, and dark matter between us and the center, and all the mass at similar and greater distances. The dominant gravitational influence comes from the galaxy as a whole. All those hundreds of billions of stars distributed throughout the disk and bulge, all the gas and dust in the interstellar medium, and crucially, the dark matter halo that extends far beyond the visible boundaries of the galaxy in an enormous, roughly spherical distribution. Dark matter is one of the quieter mysteries of modern astrophysics. Quiet in the sense that it makes itself known, not through any dramatic signal, but through the gentle, consistent discrepancy between what we can see and what the gravitational evidence tells us must be there. The rotation curve of the Milky Way, the pattern of orbital velocities at different distances from the galactic center, does not behave the way it would if the mass of the galaxy were concentrated where the visible light is concentrated. If only the visible stars and gas were responsible for the galaxy's gravity, orbital velocities would decrease at large distances from the center, just as the orbital velocities of the outer planets in our solar system decrease with distance from the Sun. Instead, the orbital velocities remain roughly constant, far out into the disk and beyond, suggesting that there is a much larger, more extended mass distribution surrounding the galaxy, one that we cannot see, but whose gravitational influence is undeniable. This dark matter halo is estimated to contain several times as much mass as all the visible stars and gas in the galaxy combined. It extends to distances hundreds of thousands of light-years from the galactic center, far beyond the farthest visible stars of the Milky Way. Its distribution is roughly spherical in contrast to the flattened disk of the visible galaxy, and it provides the gravitational scaffolding that holds the disk together and governs the orbits of stars and the solar system at large distances from the center. We do not know what dark matter is made of. Decades of experiments designed to directly detect dark matter particles have returned null results, or results too ambiguous to constitute a confirmed detection. The leading theoretical candidates are exotic particles that interact with ordinary matter only gravitationally and through the weak nuclear force, so-called WIMPs, or weakly interacting massive particles. But no confirmed detection of such particles has been achieved despite increasingly sensitive detectors buried deep underground, operated in low background environments, and monitored for years. Alternative theories, modified gravity, warm dark matter, axions, primordial black holes continue to be explored and tested. The nature of dark matter remains one of the most important and most genuinely open questions in all of contemporary physics. What is important for our thought experiment is that the gravitational landscape in which the solar system orbits the galaxy is shaped in large part by this invisible component, and that removing the solar system's orbital velocity would leave it in the grip of this total gravitational field, the combined pull of visible and dark matter, without the balancing inertia to maintain its circular path. The result, as we discussed, would be an inward fall toward the galactic center, proceeding over millions of years, gradually drawing the solar system from its current quiet and relatively sparsely populated region of the outer disk toward the increasingly dense and complex environment of the inner galaxy. In the early stages of this inward drift, the solar system's environment would change only subtly. The stellar density in our current galactic neighborhood, the Orion Arm or Orion Spur, a modest spiral arm feature between the larger Sagittarius and Perseus arms, is not dramatically different from the average density across the disk at our distance from the center. As the solar system drifted inward, the density of neighboring stars would gradually increase, and the rate of close stellar encounters close enough to gravitationally perturb the outer reaches of the solar system would begin to rise. The Oort cloud, the vast and distant reservoir of comets that surrounds our solar system at distances of thousands to tens of thousands of astronomical units from the Sun, is the part of the solar system most vulnerable to these gravitational perturbations. Individual comets in the Oort cloud are so weakly bound to the Sun at such enormous distances that even the gravitational nudge of a passing star at several light-years distance can alter their orbits significantly, sending some of them on long, falling paths into the inner solar system, where they eventually become visible as the bright, slow-moving objects that have been watched with fascination since the beginning of human history. In a denser, stellar environment, these perturbations would be more frequent and more powerful, and the rate at which comets were delivered to the inner solar system would increase. A higher cometary flux would increase the probability of impacts on Earth and the other inner planets. Not dramatically in the short term, but significantly over the millions and tens of millions of years, during which the inward drift continued. The geological and biological history of Earth is already marked by impact events of varying severity, and the extraordinary extinction event 66 million years ago, which ended the reign of the non-avian dinosaurs and opened the world to the diversification of mammals, is widely attributed to the impact of a large body from the outer solar system. An increased cometary flux would mean an increased frequency of such events, and over long timescales, this could fundamentally alter the trajectory of life on Earth. But even more significant, eventually, would be the changing radiation environment. The inner galaxy contains a higher density of massive young stars, stars that live fast and die spectacularly in supernova explosions that release enormous quantities of energy and produce powerful bursts of gamma radiation and X-rays. At sufficient distances, these supernovae are simply interesting astronomical events. But at sufficiently close range, within tens of light years, a supernova could expose Earth to radiation levels that would damage the ozone layer, exposing the surface to elevated ultraviolet radiation for years or decades, and potentially triggering significant disruptions to the biosphere. Some researchers have proposed that past mass extinction events on Earth may be connected to nearby supernovae, though this remains speculative and the evidence is difficult to evaluate definitively. As the inward drift continued over tens of millions of years, the solar system would pass through regions of the galaxy with increasing stellar and gas density, encounter the spiral arms more frequently, and experience an environment progressively less similar to the quiet outer disk we currently inhabit. Eventually, after a journey of perhaps 100 million years or more, the solar system would be approaching the inner galaxy, a region whose conditions are quite different from anything the solar system has encountered in its long history. And all of this entire slow, gradually unfolding transformation of the solar system's cosmic context would be the consequence of removing the galactic orbital velocity, a change that would have been completely imperceptible to anyone on the surface of Earth for many millions of years after it occurred. This contrast between the immediate consequences of removing the solar orbital velocity and the glacially slow consequences of removing the galactic orbital velocity is, in itself, one of the most instructive things about the nested structure of our cosmic home. We are most tightly coupled to the gravity of the Sun. It is the dominant gravitational influence on our daily existence, on the seasons and the years and the climate. We are much more loosely coupled to the gravity of the galaxy as a whole, and the consequences of disrupting that coupling unfold on timescales so long that they are simply outside the scope of any human experience or planning. Let us now think about the next layer outward, the motion of the Milky Way within the local group and the larger cosmic web. The local group is a small but real gravitational community. The Milky Way and Andromeda are its dominant members, but there are dozens of smaller galaxies, dwarf galaxies of various types, irregular galaxies, small spirals, distributed throughout the volume. Many of these smaller galaxies are satellites of the Milky Way or Andromeda, in orbit around one or the other in the way that moons orbit planets. Though the orbits operate on timescales of billions of years, and the dynamics are considerably more complex than simple two-body Keplerian motion. The Andromeda galaxy, at a distance of approximately 2.5 million light-years, is the most prominent member of the local group after the Milky Way itself. It is a large spiral galaxy, somewhat more massive than our own, and it is the most distant object visible to the naked eye from a dark site. A faint, elongated smudge in the autumn sky of the northern hemisphere, easily overlooked, but quietly remarkable when you know what you are seeing. An entire galaxy containing hundreds of billions of stars, so far away that the light reaching your eyes left it 2.5 million years ago, when our ancestors on Earth were still Homo habilis, early stone tool users just beginning the long journey that would eventually lead to the species capable of looking up and recognizing that fuzzy patch of light for what it is. Andromeda and the Milky Way are falling toward each other. Their mutual gravity has overcome the expansion of space at this scale. The local group is a bound structure, large enough to be gravitationally self-contained in the face of the universal expansion. And the two galaxies are currently approaching each other at roughly 110 kilometers per second. In approximately 4 billion years, give or take, they will begin to interpenetrate. The collision, when it comes, will not be a violent impact in any ordinary sense. Galaxies are mostly empty space, and the stars within them are so distant from one another that direct stellar collisions during a galactic merger are extraordinarily rare. Instead, the merger will be a slow, gravitational dance. The two galaxies passing through each other, distorting each other into spectacular shapes, triggering bursts of star formation as gas clouds collide and compress, and eventually settling into a single merged galaxy, likely an elliptical galaxy without the elegant spiraled structure of either parent. After hundreds of millions of years of interaction, the Sun will almost certainly survive this process, though its position in the merged galaxy may be quite different from its current location. Earth, if it still exists in anything recognizable form, which depends on whether the Sun has yet entered its red giant phase, which will occur in roughly 5 billion years, would have a night sky transformed beyond recognition, filled not with the familiar Milky Way band, but with the complex, chaotic structure of a merging galaxy system, with Andromeda's stars scattered across the sky in great arcing streams of light. This future merger is a vivid reminder that the Milky Way's motion within the local group is not merely an abstract cosmological fact. It is the current chapter in an ongoing story of gravitational interaction that has been developing since the local group formed, and it will continue developing in ways that will, over the deep future, fundamentally transform the cosmic environment of our solar system. If the motion of the Milky Way through the local group, the component that is not simply the Hubble flow, but the actual peculiar velocity arising from gravitational interaction, was suddenly removed, the dynamics of the Andromeda-Milky Way approach would change. Without the Milky Way's current velocity, the two galaxies might approach each other on a slightly different trajectory, or the timing of the eventual merger might shift. The details would depend on the precise velocity and direction removed, and the consequences would unfold on the same billion-year timescales as the merger itself. Again, the change would be utterly imperceptible on any human timescale. Beyond the local group, the motion of our galactic community through the cosmic web, the slow drift toward the great attractor, and the larger-scale flow associated with the Shapley supercluster, represents the deepest layer of Earth's motion through space that we can meaningfully discuss. These motions, at hundreds of kilometers per second, are embedded in the large-scale structure of the universe, the pattern of galaxy filaments, sheets and voids that formed over billions of years through the gravitational amplification of tiny density fluctuations that were already present in the universe a fraction of a second after the Big Bang. The cosmic web is one of the most beautiful and largest scale structures in all of nature. Visualized in 3 dimensions, it looks like a vast foam or sponge. Enormous voids, nearly empty of galaxies, separated by thin sheets and filaments, along which galaxies and galaxy clusters are concentrated like dew on a spider's web. The filaments cross and intersect at nodes where the densest galaxy clusters are found, and the whole structure extends across the observable universe in a pattern that is, on the very largest scales, statistically uniform, the same in every direction and in every region, but richly varied in its local details. The great attractor toward which our local group is drifting is a concentration of mass at the intersection of several such filaments, a node in the cosmic web where the density of galaxies and dark matter exceeds the average by a substantial factor. The gravitational pull of this concentration extends outward over hundreds of millions of light years, drawing galaxies and galaxy clusters slowly toward it in the same way that the Sun draws planets. The motion is slow, covering hundreds of millions of light years over billions of years. But it is real, and it is one of the reasons why the cosmic microwave background appears slightly asymmetric as seen from Earth. If all of this motion were removed, if the local group were brought to rest relative to the CMB, the only immediate effect, again, would be a very slow change in trajectory as the gravitational pull of the great attractor and the repulsion of nearby voids began to pull the now stationary local group in their preferred directions. The timescale for any significant change in position would be measured in hundreds of millions to billions of years. For anyone on the surface of Earth, in any conceivable human context, there would be no perceptible difference whatsoever. And this is where the thought experiment arrives at one of its most philosophically interesting destinations. We have now traced all the layers of Earth's motion through space and asked what removing each one would mean. The innermost layer, the orbital motion around the Sun, is the one with the most immediate and dramatic consequences, because it is the one governed by the most powerful gravitational relationship in Earth's direct experience. The outer layers, galactic orbit, local group motion, bulk cosmic flow, have consequences that operate on timescales so vast as to be effectively invisible from any human vantage point. The lesson, if we choose to draw one, is about the nested structure of gravitational influence. We are intimately connected to the Sun, deeply shaped by it, utterly dependent on our orbital relationship with it for the stability of climate and the continuity of the seasons. We are much more loosely connected to the larger gravitational structures. Connected, yes, embedded in them, shaped by them in subtle ways over geological and cosmic timescales, but not immediately dependent on them in the same moment-to-moment way that we depend on the Sun's gravity. This hierarchy of gravitational influence is one of the most structurally important features of our cosmic situation, and it is why the thought experiment of stopping Earth's motion through space produces such different answers depending on which scale of motion you are asking about. Now let us turn our attention for a while to the deeper physics of motion, gravity, and space-time, to the theoretical framework that underlies all of the scenarios we have discussed and that reveals the most profound truths about the nature of the cosmos we inhabit. General relativity, Einstein's theory of gravity, describes the universe in terms of a four-dimensional space-time. 3 dimensions of space and 1 of time, woven together into a single mathematical fabric. In this framework, mass and energy do not simply exert forces on other objects at a distance. They curve the space-time fabric itself, and other objects respond by moving along the straightest possible paths through this curved geometry. What we experience as gravity is not a force at all in the deepest sense, but the geometry of space-time in the neighborhood of a massive object, the simple consequence of moving through a curved space. An orbit in this picture is a geodesic, the curved space-time equivalent of a straight line. Just as a straight line on the surface of a sphere is actually a great circle, the shortest path between 2 points on a sphere, the natural free-fall path in the curved space-time around a star is an ellipse. Earth follows this ellipse not because any force is pushing or pulling it, but because the ellipse is the natural, effortless path through the space-time shaped by the Sun's mass. If you were aboard a spacecraft in Earth's orbit and you switched off your engines, you would float freely, feeling no force, following the same curved space-time path as Earth. And you would remain in that orbit indefinitely, following the geometry of space-time until some external influence perturbed you. This is the deep reason why astronauts in orbit feel weightless. They are not beyond gravity. They are in the midst of it, following a geodesic through curved space-time in exactly the same state of free fall as everything else in orbit. The feeling of weight we experience on Earth's surface is not due to gravity pulling us down. It is due to the surface pushing us up, deviating us from the free fall geodesic that would otherwise carry us toward Earth's center. The ground under our feet is, in the relativistic sense, continuously accelerating us upward, away from the natural free fall path. And that upward acceleration is what we experience as the sensation of weight. This counterintuitive insight that we feel weight not when we are in gravity's grip, but when we are being pushed away from free fall, is one of the most elegant and strange consequences of general relativity. And it changes the way we think about what it means to stop Earth's motion through space. In the relativistic picture, stopping Earth's orbital motion means taking Earth off its geodesic, moving it from its natural free-fall path and placing it at rest relative to the Sun. From that moment, the natural geodesic at Earth's new location would carry it directly toward the Sun, and it would follow that inward geodesic just as naturally and effortlessly as it had followed the orbital ellipse before. Gravity does not need to exert itself to pull Earth toward the Sun. It simply needs for Earth's velocity to be removed, and the geometry of space-time does the rest. This picture of gravity as geometry rather than force is not merely a mathematical reformulation of the same physics. It makes predictions that differ from Newtonian gravity in subtle but measurable ways, and those predictions have been confirmed in every test to which general relativity has been subjected. The bending of light by the Sun, the gravitational redshift of light climbing out of a gravitational well, the precession of the perihelion of Mercury's orbit, the existence of gravitational waves, all of these were predicted by general relativity and have been observed, the last of them directly detected for the first time in 2015, when the LIGO Observatory measured the space-time ripple produced by the merger of two black holes over 1 billion light-years away. Gravitational waves are themselves a consequence of the fact that gravity is geometry. When massive objects accelerate, when two black holes spiral together and merge, when two neutron stars collide, when any sufficiently massive and asymmetric system undergoes rapid changes in configuration, the curvature of space-time propagates outward as waves, much as disturbances on the surface of water propagate as ripples. These waves travel at the speed of light, stretch and compress space as they pass, and carry energy away from the emitting system. Their detection opened an entirely new window onto the universe, allowing astronomers to observe events that produce no light, but do produce these space-time ripples, mergers of compact objects, certain kinds of supernova explosions, potentially even echoes of processes in the very early universe. Earth itself, moving in its orbit around the Sun, produces a tiny amount of gravitational radiation. The acceleration of such a massive object through such a deep gravitational field does generate space-time ripples, though at an amplitude so vanishingly small that no conceivable instrument could detect them. The system radiates away a negligible amount of orbital energy through gravitational waves, causing Earth to very, very slowly spiral inward over timescales, that are many orders of magnitude longer than the current age of the universe. For all practical purposes, this effect is completely irrelevant. But it is real, and it is another reminder of the deep unity between orbital motion and the structure of space-time itself. Now, let us think about the role of time in all of this. Because time is one of the most intimate companions of motion, and the thought experiment of stopping Earth's motion opens naturally into questions about the nature of time and its relationship to the physical world. In Newton's universe, time was absolute and universal. It flowed at the same rate everywhere, independent of any observer or any physical process. The time experienced by a person on Earth, by an astronaut on the Moon, by a hypothetical observer at the edge of the galaxy, all were assumed to be identical, ticking away at the same rate, measuring the same universal progression from past to future. Einstein showed that this picture was incorrect. Time, like space, is relative. Two observers in relative motion experience time at different rates. The observer in motion experiences time passing more slowly than the observer at rest, a phenomenon called time dilation. This is not an illusion or an artifact of measurement. It is a fundamental feature of the universe. Atomic clocks flown on aircraft and then compared to identical clocks left on the ground show a real measurable difference in the amount of time elapsed. The clocks that traveled have ticked more slowly by exactly the amount predicted by special and general relativity. There are actually two types of time dilation relevant to Earth's situation. The first is the time dilation due to motion, special relativistic time dilation, which causes clocks in motion to run more slowly than clocks at rest, with the effect becoming significant when the velocity is a substantial fraction of the speed of light. Earth's orbital velocity of 30 kilometers per second is only about 0.01% of the speed of light, so the special relativistic time dilation is tiny but measurable. The second is the time dilation due to gravity. Gravitational time dilation, a consequence of general relativity, which causes clocks deeper in a gravitational well to run more slowly than clocks farther out. For Earth, both effects are present. The surface of Earth is moving at some velocity, both orbital and rotational, and it is also deeper in the Sun's gravitational well than, say, a distant spacecraft. The GPS satellite system, which relies on extremely precise atomic clocks, must account for both types of time dilation to maintain the accuracy that makes navigation possible. The satellite's clocks run faster than clocks on the ground because they are higher up in Earth's gravitational well, and they run slower because they are in motion. The net effect is a small but significant correction that the system's software applies continuously. If Earth's orbital velocity were removed, if it were brought to rest relative to the Sun and then fell inward, the time dilation experienced by objects on Earth's surface would change as Earth approached the Sun. Deeper in the Sun's gravitational well, time would run slightly more slowly. At Earth's current distance from the Sun, the gravitational time dilation is already tiny but present. At closer distances, it would increase. This is a very small effect in the context of everything else happening during the inward plunge. But it is real, and it illustrates the deep connection between motion, gravity, and time that lies at the heart of general relativity. The philosophical implications of time dilation are profound and somewhat vertiginous if you let them be. but they also have a certain quieting quality. A reminder that time is not the fixed universal river that our intuitions suggest, but something more subtle, more flexible, more fundamentally woven into the fabric of space and matter than Newton imagined. We are not moving through time in the way we move through a room. We are co-creating our experience of time through our own motion and our position in gravitational fields. And every object in the universe has a slightly different experience of time, depending on its trajectory and its location. This is one of the quieter revelations of modern physics, that the universe does not have a single universal clock, that simultaneity is not an absolute fact, that the question of whether two events happen at the same time is a question that different observers can answer differently and both be correct. It is a realization that requires a certain loosening of the grip on familiar intuitions, a willingness to follow the mathematics into terrain that our everyday experience has not prepared us for. But it is also a realization of extraordinary fertility. It is the foundation on which the entire modern understanding of space-time, black holes, gravitational waves, and the large-scale structure of the universe is built. Let us now consider the specific scenario of our thought experiment from the perspective of an observer watching from outside, from a hypothetical position somewhere far from the solar system, watching Earth suddenly cease its orbital motion and begin to fall toward the Sun. Such an observer, equipped with sufficiently sensitive instruments, would first detect the event through its gravitational consequences. When Earth suddenly changed its velocity, went from 30 kilometers per second in one direction to 0, the gravitational field of the Earth-Sun system would change, and that change would propagate outward as a ripple in space-time, traveling at the speed of light. Our hypothetical observer, at some distance from the solar system, would not immediately see Earth stop. They would see it continue to move for as long as it took the light to travel from the solar system to their location. Only after that delay would the news of the event arrive. But here is something interesting. In addition to the ordinary light carrying images of Earth's new position and trajectory, the sudden change in Earth's velocity would also generate a tiny pulse of gravitational radiation, a ripple in space-time produced by the rapid change in Earth's momentum. This pulse would be extraordinarily faint, far below the sensitivity of any instrument we could currently build. But it would be real. It would carry information about the event, about the magnitude and direction of the velocity change, about the mass of the object involved, encoded in the shape of the space-time ripple. This illustrates one of the remarkable implications of general relativity, that every change in the motion of any massive object sends ripples through the fabric of space-time, carrying information about the event outward at the speed of light. The universe is, in a sense, continuously broadcasting the gravitational news of everything that happens within it, in a medium that passes through all matter and is only very weakly absorbed or scattered. Detecting these ripples requires extraordinarily sensitive instruments. The LIGO detectors are sensitive to changes in distance smaller than 1,000th the diameter of a proton. But the ripples themselves are always there, an endless outward spreading record of every gravitational event in the history of the universe. Let us turn now to a different aspect of the thought experiment. The question of what would happen not just to Earth, but to the other objects in the solar system if Earth's motion were removed. The solar system is a dynamically interrelated collection of objects. The planets interact gravitationally with each other, not just with the Sun, and these interactions produce the subtle but real perturbations in planetary orbits that astronomers call resonances and perturbations. The most dramatic of these involve Jupiter, by far the most massive planet in the solar system, whose gravitational influence is felt throughout the planetary system and beyond. Jupiter's gravity is responsible for the gap structure of the asteroid belt, the Kirkwood gaps where the density of asteroids is reduced, because orbits in those regions are in resonance with Jupiter's orbital period and are therefore destabilized. It is also responsible for sending some comets and asteroids on Earth-crossing trajectories through complex chains of gravitational perturbations that can take millions of years to unfold. If Earth was suddenly removed from its orbit, or its velocity removed, causing it to begin an inward fall, the gravitational influence of Earth on the other planets would change. Earth's absence from its normal orbital position would slightly alter the gravitational tugs experienced by Venus, Mars, and Mercury, and the effects of these alterations would propagate through the solar system's intricate gravitational web over time. The changes would be modest. Earth is not the most massive object in the solar system, and its direct gravitational influence on the other planets is small compared to Jupiter's. But over long timescales, the solar system's orbital dynamics would evolve differently without Earth in its normal place. The Moon, of course, would be the most immediately and dramatically affected object. Currently in orbit around Earth, the Moon would find itself in a quite different situation once Earth began its inward fall. The Moon, being in orbit around Earth, would be carried along by Earth's gravitational influence. It too would have had its orbital velocity removed in our thought experiment. Or it would not, depending on the precise formulation. If we imagine only Earth's velocity being removed, while the Moon's velocity relative to Earth remains intact, then the Moon would initially continue to orbit Earth normally, while Earth fell toward the Sun. But as Earth fell inward and the gravitational landscape changed, as Earth entered regions closer to the Sun, where solar tidal forces on the Earth-Moon system became stronger, the Moon's orbit would be perturbed. Eventually, as Earth approached the Sun closely enough, the tidal force of the Sun on the Moon would exceed Earth's gravitational hold, and the Moon would be stripped from Earth's orbit and placed on its own path around the Sun. This separation of the Moon from Earth, which would happen gradually over the weeks of Earth's inward fall, with the precise timing depending on the Moon's orbital position at the moment of the event, would be one of the more poignant consequences of the thought experiment, in a manner of speaking. The Moon has been Earth's companion for 4.5 billion years, formed from Earth's own substance in the violence of the Theia impact, gradually spiraling outward over geological time as tidal interactions transferred angular momentum from Earth's spin to the Moon's orbit. The permanent bond between these two worlds, old as the solar system itself, would be broken by the same gravitational mechanics that had shaped it. But let us not become too attached to the dramatic imagery of these scenarios. Our purpose tonight is not to dwell on catastrophe, but to use the thought experiment as a lens through which to see the physics and the cosmos more clearly. Each scenario we have explored, the fall toward the Sun, the inward galactic drift, the changing cosmic context, is interesting, not because of what it destroys, but because of what it reveals. The gravitational architecture of our solar system, the layered structure of cosmic motion, the deep principles of inertia and orbital mechanics and space-time geometry that govern everything from the smallest laboratory experiment to the largest structures in the observable universe. And now, having spent a long and patient evening working through the physical consequences of our thought experiment, let us begin to move toward the philosophical dimensions, toward the questions of meaning and scale and time that the thought experiment naturally opens. One of the most quietly remarkable things about the universe is that it is comprehensible at all. The equations that describe the motion of planets were first worked out by human beings, creatures with a lifespan of less than a century, living on a small rocky world in an unremarkable corner of a large galaxy, sitting at tables, working with quill pens or chalk on blackboards, reasoning from observations and mathematics toward laws that turned out to apply not just to the solar system, but to every star, every galaxy, every black hole in the observable universe. This is not something the universe was required to make possible. There is no a priori reason why the mathematical structures that describe planetary motion should be the same ones that describe the curvature of space-time around a supermassive black hole 15 billion light-years away. And yet they are. The same equations work, the same principles apply. This universality of physical law is one of the most profound and least fully explained facts about the universe we inhabit. It suggests, though it does not prove, that the universe has a deep mathematical structure, a kind of rational architecture that is the same everywhere and at all scales, from the subatomic to the cosmological. This mathematical structure is what makes science possible, what allows a small and finite intelligence to deduce the properties of systems too large and too remote for any direct contact. Without it, the universe would be opaque, every place different, every scale governed by different rules, no possibility of inference from the local to the distant or from the present to the past and future. With it, we can sit in a small room on a small planet and deduce, from the careful observation of light and the patient application of mathematics, the existence of black holes, the expansion of the universe, the temperature of the Big Bang, the composition of distant stars, the mass of invisible dark matter, the accelerating expansion driven by dark energy. We can look at the subtle asymmetry of a microwave background temperature map and read from it our own velocity through the cosmos. We can watch a black hole merge a billion light-years away as a brief ripple in the length of a laser beam. We can, in short, comprehend the universe far beyond the boundaries of what we can directly experience. This is the quiet miracle that lies at the heart of science, and it is what makes thought experiments like the one we have been exploring tonight so valuable. The question of what would happen if Earth stopped moving through space cannot be answered from direct experience. Earth has never stopped, will never stop, and we have no experimental data on the matter. But we can answer it with confidence nonetheless, because we understand the principles that govern motion and gravity well enough to extrapolate with accuracy to scenarios we have never witnessed. The laws of physics, tested and confirmed in laboratories and observations across centuries, allow us to reason beyond the limits of experience, to explore hypothetical universes and extract real truths about the actual one. There is something deeply satisfying about this. The universe, in giving us minds capable of understanding it, seems to have done something gently extraordinary. created objects that can, at least partially, comprehend the whole. We are made of the same atoms as stars, governed by the same physics as galaxies, and capable, through patient observation and careful reasoning, of constructing a picture of reality that extends from the quantum scale to the cosmic horizon. We are small, certainly, but we are not without some participation in the grandeur of what we inhabit. Let us now think about the question of scale in a slightly different way, not in terms of distances and velocities, which we have discussed at length, but in terms of time. The temporal scales involved in the nested motions of Earth through space are, in their own way, as staggering as the spatial ones. Earth's rotation takes about 24 hours. A day, the most fundamental unit of human time, the rhythm around which civilization has organized itself since before history. Earth's orbit around the Sun takes about 365 days. A year, the second most fundamental unit, the cycle of seasons and agriculture, and the counting of ages. These two timescales are so deeply embedded in human life that we rarely think of them as physical facts about the solar system. They simply feel like the natural rhythm of existence. But the galactic year, 225 to 250 million years, is a timescale that has no human equivalent, no cultural parallel, no lived experience to anchor it. In a single galactic year, the solar system sweeps through 250 million years of time. During the most recent galactic year, the solar system has witnessed the entire reign of the dinosaurs from their earliest appearance to their final extinction. The subsequent diversification of mammals, the cooling of the planet through successive ice ages, and the entire span of human evolution from the earliest recognizable members of our genus to the civilization that now looks back at all of this history in fossil records and genetic archives. All of that, the entire deep history of complex animal life as we know it, fits within a single galactic year. 2 galactic years ago, the solar system was in a position roughly equivalent to its current one. 2 trips around the Milky Way back, and on Earth, the Permian period was ending in the greatest mass extinction in the history of complex life, a catastrophic event that wiped out more than 90% of marine species and more than 70% of terrestrial vertebrate species. The causes of this extinction are still debated, but it was almost certainly connected to massive volcanic activity in what is now Siberia, producing a prolonged and dramatic alteration of Earth's climate and ocean chemistry. The world that emerged from that extinction was impoverished compared to what came before, but it was the world from which all subsequent complex life, including our own lineage, ultimately descended. A single galactic year separates us from that event. 10 galactic years ago, the solar system was witnessing the earliest complex multicellular life, the strange soft-bodied organisms of the Ediacaran period, creatures unlike anything alive today, experimenting with forms and body plans that were largely swept away before the Cambrian explosion that followed. And 20 galactic years ago, Earth had barely formed at all, still in the violent early stages of its existence, its surface a churning mix of magma and impact craters, its atmosphere a thick reducing shroud of methane and ammonia and carbon dioxide, with no free oxygen and no possibility yet of complex life. These correspondences between galactic years and geological periods are not exact, and there is no direct causal connection implied. The galactic orbit is not a clock that drives geological events in any simple mechanical way, but as a frame for appreciating temporal scale the comparison is quietly illuminating. The same number of orbits around the Sun that a human life contains, roughly 70 to 80, is a number so small relative to the galactic year that it would occupy a fraction of a single day if the galactic year were compressed into a human lifetime. We live in the briefest of flickers within the rhythm of the galaxy's turning, and the universe itself, 13.8 billion years old, represents approximately 55 galactic years in its entirety. The Milky Way formed roughly 13 billion years ago, meaning it has completed around 52 orbits of its own structure since it coalesced from the primordial gas. The solar system, at 4.6 billion years old, has completed roughly 18 to 20 of those orbits. We are, in galactic terms, a relatively young system in a relatively old galaxy, living at a moment in cosmic history when stars and planetary systems like ours are still forming in abundance, when the universe is still in its productive star-forming phase, still rich with the elements and energies that make planetary systems and biological complexity possible. This will not always be the case. In the very long future, in timescales measured not in millions or billions, but in trillions of years, the universe will gradually exhaust its star-forming gas. The existing stars will age and die, and the galaxies will become increasingly dark and cold as the last stellar fires go out. The expansion of the universe, accelerating under the influence of dark energy, will carry the remnants of galaxies beyond each other's horizons, leaving each isolated in an expanding void. The universe of the far future will be a quiet, dark, cold place, very different from the richly structured, star-filled cosmos we inhabit today. We live at a privileged moment in cosmic history, not in any cosmically special sense. We did not choose this moment, and there is no plan that placed us here. But in the sense that now, during the stelliferous era, the universe is at its most hospitable to the formation of planets and the development of life and intelligence. The elements heavier than hydrogen and helium that make rocky planets possible, carbon, oxygen, nitrogen, iron, silicon, and all the rest, were forged in previous generations of stars and scattered into space by supernova explosions over billions of years of stellar evolution before the solar system formed. We are, in a real and not merely metaphorical sense, the children of dead stars, made from the material they spent their lives creating and then graciously returned to the cosmos for future use. This is one of the most profound and most gently humbling truths of modern astrophysics. The atoms in your body, the carbon in your cells, the oxygen in your blood, the iron in your hemoglobin, were synthesized inside stars that died before the sun was born. They were scattered into the interstellar medium, mixed with gas and dust over millions of years, and eventually incorporated into the cloud that collapsed to form the solar system. The same atoms that spent millions of years inside a stellar core, participating in nuclear reactions that generated the star's light, now make up the structure of your thoughts, the warmth of your breath, the weight of your hands folded quietly in your lap as you listen. There is something in this truth that dissolves the boundary between self and cosmos in a way that no philosophical argument can quite replicate. We are not observers of the universe looking in from outside. We are the universe observing itself from within, made of the same substance as everything else, governed by the same physics, participating in the same great unfolding story. The question of what would happen if Earth stopped moving through space is, in the deepest sense, a question about ourselves, about what we are, where we are, what holds us in place and keeps us warm and makes our existence possible. And the answer, traced through all the layers we have explored tonight, is that we are held in place and kept warm by a cascade of gravitational relationships. From the immediate warmth of the sun at 150 million kilometers to the vast and invisible gravitational scaffold of the galaxy's dark matter halo that operates across scales ranging from the mundane to the cosmological, all governed by the same equations, all expressing the same fundamental reality. To stop moving through space, in the most complete sense, would be to dissolve all of these relationships simultaneously, to sever every gravitational bond, to erase every orbital balance, to leave Earth as a genuinely isolated object in an empty universe. And in that impossible scenario, stripped of every relationship that defines it, Earth would simply be an object in space, cooling slowly toward the temperature of the cosmic background, its internal heat gradually leaking away into the void, its atoms persisting, but its structure, its warmth, its life, all slowly dissolving into the quiet equilibrium of an isolated rock in an empty universe. This is the extreme limit of the thought experiment, and it is, in some sense, its most honest conclusion. Earth is not Earth in isolation. Earth is Earth in relationship, with the sun, with the moon, with the other planets of the solar system, with the galaxy that contains us, with the cosmic web that contains the galaxy. Remove all the motion, all the relationships, all the gravitational connections, and what remains is still a very beautiful arrangement of atoms. But it is no longer the living, turning, orbiting, season-cycling, life-bearing world that we know. Our motion through space is not incidental to our existence. It is constitutive of it. The Earth we know is the Earth that moves. Now let us allow the thought experiment to dissolve into something gentler, into the simple, quiet appreciation of the actual universe as it is. With all its motion and its relationships intact, its orbits unbroken, its layers of nested movement humming along as they have for billions of years and will continue to do for billions more. Right now, as these words settle into the quiet of your evening, Earth is turning. The terminator, the line between day and night, is sweeping across some part of the planet's surface, carrying the sunrise to some people and the sunset to others. The oceans are catching the light at some angles, reflecting it at others, their surfaces stirred by winds driven by the temperature gradients created by that same sunlight, falling unevenly on a turning sphere. The atmosphere is in motion, great convective cells rising and falling, jet streams winding around the planet in their meandering paths, weather systems forming and dissipating in patterns of extraordinary complexity. Beneath the surface, the liquid iron of the outer core is flowing in complex, turbulent patterns, driven by the heat escaping from the inner core and by the rotation of the planet, generating the electric currents that maintain Earth's magnetic field, the invisible shield that deflects the solar wind and protects the atmosphere and the surface from the full force of solar radiation. The tectonic plates are moving, slowly but continuously, carrying the continents with them in their long geological dance, building mountains where they collide, creating ocean floor where they pull apart, recycling the surface of the planet in a process that has been ongoing since the early days of Earth's history and that has profoundly shaped the chemical composition of the atmosphere and the history of life. At the same time, Earth is moving in its orbit around the Sun at 30 kilometers per second, silently, smoothly, without any sensation of the motion, carrying all of this turning, churning, living complexity through the solar system on the path it has followed for 4.54 billion years. The Sun is ahead of us in the direction of our current orbital motion, not quite ahead, but at some angle that depends on the season. And it is behind us in another direction, and in 12 months we will be back approximately where we are now, having traced the full ellipse of the year. Meanwhile, the solar system as a whole is sweeping through the Milky Way at 220 to 250 kilometers per second, carrying Earth and Sun and Moon and all the planets and moons and comets and asteroids through the vast, mostly empty space between the stars. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away, roughly 40 trillion kilometers. And even at the solar system's galactic orbital velocity, it would take many tens of thousands of years to cover that distance. The galaxy is not a crowded place. It is mostly void, with stars separated by distances so enormous that the average solar system has no meaningful interaction with any other for millions of years at a time. And the Milky Way itself is drifting through the local group, its disk of stars and spiral arms sweeping through the sparse intergalactic medium that fills the space between galaxies, on a long course that will eventually bring it into the gentle embrace of the Andromeda Galaxy. That encounter lies billions of years in the future, and neither the Sun nor the Earth is likely to exist in recognizable form when it occurs. The Sun will have exhausted its hydrogen fuel and expanded into a red giant long before then, gently engulfing the inner planets and radically transforming the solar system. But the event is written into the gravitational destiny of the local group as inevitable and as peaceful in its own enormous way as the turning of the seasons. All of this motion, the spin, the orbit, the galactic sweep, the cosmic drift, is happening right now, silently and continuously, without any engine to maintain it and without any sign of stopping. It has been happening for billions of years and will continue for billions more. It is the deep, quiet pulse of the physical universe, the expression of conservation laws so fundamental that they have not been violated once in all of observable history. There is something deeply restful in this if you allow yourself to feel it. Not restful in the sense of stillness. The universe is anything but still, but restful in the sense of reliability. The orbits continue, the laws hold. The conservation of angular momentum, the conservation of energy, the principle of relativity, these are not provisional or fragile. They are the stable, unchanging foundation of the physical world, as consistent and trustworthy as anything in our experience. Earth will be in approximately the same place in its orbit next year that it is this year. The Sun will be approximately where it is expected to be in the galaxy. The Andromeda Galaxy will be approximately as far away as the equations predict. The universe, for all its complexity and its vastness, is lawful, and the laws are ones we have learned to read. We have spent a long evening with this question. What would happen if Earth stopped moving through space? And we have traced it from its simplest physical implications, through layers of increasing depth and scale, to the edges of philosophy and cosmology. We have seen how the question, seemingly simple, opens into the full complexity of gravitational physics, space-time geometry, the structure of the Milky Way, the dynamics of the local group, the large-scale structure of the universe, and the deepest principles of relativity and conservation. We have seen that the consequences of stopping Earth's motion depend entirely on which layer of motion we remove. That removing the orbital velocity around the Sun produces immediate and dramatic consequences over days and weeks, while removing the galactic orbital velocity produces consequences that unfold over millions of years, and removing the deepest layers of cosmic motion produces effects so slow as to be imperceptible on any human timescale. We have seen that the question of what it means to truly be at rest is one that physics answers with a principle of relativity, that there is no absolute rest, only relative motion, and that the consequences of changing motion depend on the specific gravitational relationships involved. We have also seen in exploring these scenarios something about the nature of our existence in the universe, that we are embedded in a nested structure of gravitational relationships connected to the Sun and the Moon and the planets and the galaxy and the cosmic web in ways that are mostly imperceptible to our senses, but that are entirely responsible for the stability and warmth and consistency of the world we inhabit. We are not simply on Earth. We are of Earth, and Earth is of the solar system, and the solar system is of the galaxy, and the galaxy is of the universe, all connected, all moving, all participating in the great, slow, beautiful, lawful dance of matter and energy through space-time. And now, having traveled all of this way together, from the surface of our turning planet to the edge of the observable universe and back again, it seems right to simply rest in that, to let the thought experiment settle, to let the equations and the distances and the timescales gradually soften at the edges, the way the details of a landscape soften when you let your eyes relax their focus and simply take in the whole. You are, right now, moving at 30 kilometers per second around the Sun, at 220 kilometers per second around the galaxy, at 370 kilometers per second relative to the oldest light in the universe. You are turning with the surface of the planet at whatever fraction of 1,670 kilometers per hour corresponds to your latitude. You are embedded in a gravitational web that stretches from the core of the Earth beneath you to the farthest galaxy clusters in the observable cosmos. And none of this requires any effort from you. None of it asks anything of you. It simply is as it has always been, the quiet, ongoing fact of your situation in the universe, vast and ancient and completely ordinary in the best and most reassuring sense of the word. The stars outside, if you could see them through the roof and the walls and the layers of air and light pollution between you and the sky, are moving too, each one on its own slow galactic orbit, each one carrying with it the possibility of its own planetary system, its own nested architecture of motion and gravity, perhaps its own story of matter organized into the kind of complexity that can wonder about itself. The Milky Way, if you could step outside and let your eyes fully adapt to the dark of a clear night, far from any city, arches overhead as a soft, irregular band of light. The combined glow of hundreds of billions of stars, most of them too distant to resolve individually, blending into that ancient river of light that has inspired wonder and story and scientific inquiry for as long as there have been minds capable of any of those things. And somewhere within that soft band of light, too small to see, is the place where the solar system currently resides in its galactic orbit, a quiet, unassuming location in the Orion Spur, between two spiral arms in the outer half of the disk, approximately 26,000 light-years from the center. Unremarkable by any galactic measure. And yet here, in this unremarkable place, on this small, turning planet, in this particular moment of cosmic time, something remarkable has happened. Awareness has arisen, curiosity has organized itself into science, and a species of tool-using primates has managed, through patience and ingenuity and the accumulated knowledge of many generations, to deduce the structure and the history and the laws of the universe they inhabit. That is, when you sit with it in the quiet of the night, a quietly extraordinary thing. Thank you for spending this long, unhurried evening here on the sleepy Milky Way. This channel exists because of exactly this kind of curiosity. The gentle, patient kind that asks large questions and is content to let the answers arrive slowly, without rushing toward conclusions or demanding that the universe be more dramatic than it already is. The universe, it turns out, is most remarkable when you give it time. The distances are most astonishing when you let them settle. The timescales are most moving when you stop trying to compress them into something manageable and simply let them be as vast as they are. If you have found this evening restful, if you have felt your breathing slow and your thoughts soften as the astronomy and the physics dissolved gradually into something more like a meditation on scale and motion and time, then this channel has done what it set out to do. Come back whenever you need a quiet journey. There are galaxies still to visit, phenomena still to trace slowly through their physics, questions still to ask in the patient, unhurried way that the cosmos deserves. And yet, even as we prepare to let this evening gently close, there are a few more corridors worth wandering through, a few more rooms in this vast, quiet house of cosmological understanding that we have been exploring together tonight. So let us linger a little longer, moving slowly, speaking softly, following the thought where it still wishes to go. Consider for a moment the remarkable fact that every orbit in the universe is unique. No two planets in any planetary system trace exactly the same path. No two stars in any galaxy share precisely the same galactic orbit. Even Earth's own orbit is not perfectly repeated year after year. It is subtly perturbed by the gravitational influences of the other planets, particularly Jupiter and Saturn, in ways that cause it to change shape very slowly over tens of thousands of years. These changes in Earth's orbital eccentricity, how elongated or how nearly circular the orbit is, are one of the components of what are called the Milankovitch cycles, the slow oscillations in Earth's orbital and rotational parameters that influence how solar energy is distributed across the planet's surface, and that are believed to be responsible for the rhythm of ice ages and warm interglacial periods that has dominated the climate of the last several million years. The Milankovitch cycles operate on three primary timescales. The eccentricity of Earth's orbit varies with a period of roughly 100,000 years, changing from nearly circular to slightly more elongated, and back again under the gravitational influence of Jupiter and Saturn. The tilt of Earth's rotational axis, the obliquity, varies between about 22 and 24.5 degrees, with a period of roughly 41,000 years, changing how strongly the seasons are expressed. And the direction that Earth's axis points, the precession, cycles around with a period of roughly 26,000 years, changing which hemisphere has summer, when Earth is closest to the Sun. Together, these three cycles modulate the distribution of solar energy in complex and interacting ways, and their combined rhythm appears to have been the primary driver of the glacial-interglacial cycles that have so profoundly shaped the physical and biological landscape of the late Pleistocene. This is a quietly beautiful example of how motion at one scale, the gravitational interactions of the planets in their orbits, leaves its imprint on events at a completely different scale. The advance and retreat of ice sheets across continents, the rise and fall of sea levels, the distribution of ecosystems across the planet. The connections between scales in the universe are not always obvious, but they are always there, always operating through the same fundamental physics, always tracing the same thread of cause and effect through the fabric of reality. Think also about the way light connects us to all of these different scales of motion simultaneously. The sunlight reaching your skin at any given moment left the sun approximately 8 minutes and 20 seconds ago. The sun was in a slightly different position in its orbit at the moment that light departed. Not meaningfully different, given the timescales involved, but different in principle. The light from the Andromeda galaxy that reaches your eyes on a clear autumn night left that galaxy approximately 2.5 million years ago, when our ancestors on Earth were still navigating a world shared with other hominin species. When the Milky Way and Andromeda were 2.5 million years farther apart than they are now. The light from the most distant galaxies visible to our most powerful telescopes left those galaxies when the universe was only a small fraction of its current age, when the stars were younger and the universe was smaller and denser, and the large-scale structure we see today was only beginning to emerge from the primordial density fluctuations that seeded it. We see the universe not as it is, but as it was. A different age at every distance, a layered temporal panorama spread across the sky. Looking outward is looking backward, and the two activities, exploring space and exploring time, are inseparable in a universe where light travels at a finite speed. This is one of the most profound structural features of the observable universe, that its very observability depends on the speed of light, that our picture of the cosmos is not a snapshot of a single moment, but a composite of light from countless different moments, each one corresponding to a different distance and therefore a different era. In this context, the cosmic microwave background, the faint microwave glow that fills the entire sky and encodes our own velocity through the cosmos, is the most ancient light we can observe. It comes from everywhere and from the same moment in cosmic history, the recombination epoch, approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, and space became transparent to radiation for the first time. Before that moment, the universe was opaque, a dense, hot plasma through which light could not travel freely. After it, the photons that had been trapped in that plasma streamed freely outward in all directions, and they have been traveling ever since, stretching to longer and longer wavelengths as the universe expanded around them, arriving now as the microwave background that our instruments detect with such exquisite precision. Every measurement we make of the cosmic microwave background is a measurement of the state of the universe at that single ancient moment, 380,000 years after the Big Bang, when the universe was roughly 1,000 times smaller than it is today, when the temperature was roughly 3,000 Kelvin, when the large-scale structure of the universe was encoded in tiny temperature fluctuations of about 1 part in 100,000. Those fluctuations, grown over 13.8 billion years under the influence of gravity, are the seeds of all the structure we see today. Every galaxy cluster, every cosmic filament and void, all grown from those tiny primordial ripples in the density of matter and radiation. It is a remarkable thing to contemplate, that the pattern of galaxies spread across the sky today, with all its complexity and its beauty, was already written, in potential, in seed form, in the structure of the plasma that filled the universe 1/3 of a million years after the Big Bang, and that we can read that seed structure in the microwave background and compare it to the grown structure we see in galaxy surveys, and find that they match, that the same physics that was operating in the early universe, the same gravitational amplification of tiny density fluctuations, has produced the large-scale structure we observe today. This consistency, spanning 13.8 billion years of cosmic evolution, is one of the most profound verifications of our understanding of the universe. And woven into all of this, into the cosmic microwave background, the large-scale structure, the Hubble flow, the dark matter and dark energy, is our own motion. The 370 kilometers per second that carries us toward the constellation Leo relative to the CMB. The 627 kilometers per second of the local group's bulk flow. These velocities are written in the asymmetry of the microwave sky, visible to our instruments as a slight brightening in the direction we are moving, and a slight dimming in the direction we are moving away from. We carry the record of our own cosmic motion in the oldest light in the universe, and we can read it with the same instruments we use to probe the structure of space-time from the Big Bang to the present. There is something moving about this, in the quiet, astronomical sense of the word. We are small, and the universe is large, and the motions that carry us through it are mostly imperceptible to our senses. But they are not hidden from us. They are written in the light, in the temperature of the sky, in the redshifts of distant galaxies, in the precise timings of atomic clocks, in the orbits of spacecraft sent to the outer solar system decades ago. The universe has left us all the evidence we need to deduce our own place and motion within it, if we are patient enough to look and careful enough to read. Patience is, in many ways, the most important scientific virtue, and the one most at home on a channel like this one. The great discoveries of astronomy did not come quickly. The heliocentric model of the solar system required centuries of careful observation before it was fully established and accepted. The distance to the stars required the development of parallax measurements, standard candles, spectroscopic techniques, each one building on the last over generations of patient work. The expansion of the universe was recognized only when telescopes became powerful enough to measure the redshifts of faint galaxies and the distances to them with sufficient precision. The cosmic microwave background was predicted theoretically and then discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers who initially thought the mysterious microwave signal they were detecting was noise from their equipment, and who, after carefully eliminating every other possible source, were left with the conclusion that the noise was the universe itself, speaking in microwaves from every direction equally in the voice of its own ancient past. That discovery, made through patience, rigor, and the willingness to follow the evidence wherever it led, is one of the most beautiful stories in the history of science. Two astronomers, trying to do something else entirely, stumbled upon the deepest signal in the observable universe, simply because they were careful enough not to dismiss what they did not immediately understand. The universe rewards careful attention. It always has. And the universe rewards too a certain quietness of approach, a willingness to simply be present with the complexity and the vastness without immediately demanding that it reduce to something simple, something easily summarized, something that fits comfortably within the familiar categories of everyday experience. The scales of astronomy are genuinely beyond ordinary intuition. The timescales of geology and cosmology are genuinely beyond any lived experience. The physics of relativity and quantum mechanics genuinely defies the intuitions built up through a lifetime of navigating a world of medium-sized objects moving at medium speeds. None of these things are meant to fit easily into ordinary thought, and yet they do eventually find a place, not by shrinking to fit the familiar, but by gradually expanding the familiar to accommodate them. This is what a long, patient engagement with astronomy and physics actually does over time. It does not make the scales less vast. It makes the mind more comfortable with vastness. It does not make the timescales less long. It makes the imagination more at ease with length. It gives you, slowly and gently, a different relationship with your own smallness. Not a diminished sense of self, but a richer sense of context, a more textured appreciation of the improbable and remarkable fact of your own existence in the midst of all of this. You are here, in this moment, on this turning planet, in this solar system, in this galaxy, in this universe. And the odds against any particular version of you being here in any particular moment are so astronomically large that they defy any meaningful calculation. Every contingency in the 13.8 billion year history of the universe had to unfold exactly as it did to produce you in this room, listening to this quiet voice speaking about motion and gravity and the architecture of the cosmos. The supernovae that enriched the interstellar medium with the heavy elements that became the solar system had to happen at the right times. The solar system had to form in the right part of the galaxy. Earth had to settle into the right orbit. The moon had to form from the right impact. Life had to arise and persist. Evolution had to follow its particular path through billions of years of contingent events. And the specific sequence of human generations had to unfold exactly as it did. None of this was inevitable. None of it was planned by any process we understand. It simply happened, step by step, through the ordinary operation of physics and chemistry and biology over an extraordinary span of time. And the result, improbably but undeniably, is you, here, now, in the quiet of an evening, with the cosmos laid out around you in all directions, extending to distances that no human journey will ever traverse, containing structures of beauty and complexity that no human lifetime could fully explore. The thought experiment we began this evening, what would happen if Earth stopped moving through space, has taken us a very long way from where it started. We began with a physical question, and we ended somewhere closer to a philosophical one. What does it mean to be here in motion, in relationship, in the midst of this particular universe at this particular moment in its history. The physics gives us the mechanics, the equations, the trajectories and velocities and timescales. But underneath the physics, there is something quieter, an appreciation that the motion we have been discussing is not just an abstract feature of celestial mechanics, but the very condition of our existence, the reason the seasons turn and the years pass, and the world remains warm enough for life to continue its long, intricate, improbable project. Earth moves, and because it moves, we live. The sun burns, and because it burns, we see. The galaxy turns, and because it turns, the solar system has spent its history in a relatively quiet and stable region, away from the most violent events of the galactic center, in conditions that allowed 4 billion years of biological evolution to proceed without interruption. The universe expands, and because it expands, the density and temperature of the cosmic background have decreased to the point where complexity is possible, where stars can form and burn for billions of years, where planets can cool to temperatures where chemistry becomes interesting, where life can arise and persist, and eventually look back at the universe from within. We are the universe's motion, organized into curiosity. We are the orbits and the expansions and the gravitational collapses, arranged in such a way that they can wonder about themselves. There is no more remarkable thing in all of the observable cosmos than that. And on that quiet note, as the evening deepens and the room grows softer and the words begin to dissolve at their edges, like stars seen through thin cloud, it is time to rest. Thank you, genuinely and warmly, for traveling this far tonight. Thank you for your patience with the distances and the timescales and the equations that hover just behind the words. Thank you for your curiosity, which is itself a kind of motion, a reaching outward toward what is unknown and large and beautiful. This channel exists because of exactly that curiosity, and every time you return to it, you make it a little more real, a little more worth the quiet effort of building it. If you are drifting towards sleep, then let these last words carry you there gently. The earth is turning beneath you, and the sun is somewhere below the horizon, and the stars are above you in the dark whether you can see them or not, each one continuing its slow orbit around the galaxy, each one a sun in its own right, each one moving through the cosmos in its own particular way, none of them still, none of them ever still. The whole vast turning, drifting, orbiting, expanding universe going about its ancient and beautiful business as it has for 13.8 billion years and will continue to do for incomparably longer still. You are part of all of that. You always have been. And in the morning, when the earth has turned far enough that the sun clears the horizon again and the light comes through the window, that will still be true. Sleep well, quiet traveler. The Milky Way will be here when you return.